Chapter 7, review problems, 740. All right. If a system does 45 joules of work. Here's the system, whatever, right? It doesn't tell us what the system is, but it does 45 joules of work. That means its work is moving of mass, right? So here's the mass. It did 45 joules of work. It moved this thing 45 joules worth of work. And it receives 28 joules of heat. All right? So what is the value of delta E for the change, or the change in energy? Well, 45 went out and 28 came in. All right, so that's 28 plus a negative 45, so that's a minus 17. All right, so when you read these problems, you have to look, is the work being done by the system on the surroundings or vice versa? All right, so 17.40 should be a negative 17. Let's see, where are we at? It's negative 17 joules. All right. 17.42, an automobile engine converts heat into work via a cycle. Okay. The cycle must finish exactly where it started, so the energy at the start must be exactly the same as the energy at the end. If the engine does 100 joules of work per cycle, how much heat must it absorb? Well, that has to be the same, so it's going to have to absorb 100 joules of heat if it's going to do 100 joules of work. All right, so 742 is 100. 100 joules. 744. If an engine in problem 742 absorbs 250 joules of heat per cycle, how much work can it do per cycle? 250 joules, right? 744, 250 joules. All right, so that's 744, 250. $746. How much heat in joules and in calories must be removed from 1.75 moles of water to lower the temperature from 25 to 15? 1.75 moles of water, and the temperature is going from 25 to 15, or that's 10 degrees Celsius. A change in temperature of 10 degrees Celsius, right? We can always take the final temperature, subtract the initial temperature, and that gives us our change in temperature. Temperature final minus temperature initial equals change in temperature. All right, so final is 15, initial is 20, from 25 to 15. So 15, 25, 15 minus 25, so this is going to be a negative 10 degrees Celsius, right? Or the change is 10 degrees and we want it to go down 10 degrees, right? So how much heat in joules and in calories must be removed from 1.75 moles of water? Well, there's a number in the book there, 4.184. That's how many joules per gram per degree Celsius of energy for that water needs to change 1 degree Celsius. So this is how many joules per gram that 1 degree, or to change water 1 degree Celsius. So if I have 17.5 moles of water, I can convert this to grams of water by knowing that 1 mole is 18 grams. Right? So 1.75 times 18, and that's 31.5 grams. 31.5 grams. 31.5 grams of water, 4.184 joules for every gram degrees Celsius, and we're changing 10 degrees Celsius. Okay? So the answer here would be how many joules of energy, let's see, 31.5 times 4.184 times 10. And this is how much heat in joules we would have to remove, 1317 joules. Now, it says here, how much heat in joules and in calorie must be removed, right? So if they're asking you how much heat must be removed, well, that's how much heat has to be removed, all right? The answer to this problem should have a negative in front of the 10 there, because to go final minus initial, we ended up getting a change in temperature of minus 10. And so the change in energy, or the sign indicates the change. All right, so we're discussing about when it says, I mean, at negative 10, it should be the value in here. Therefore, when the negative comes out, that means how much energy needs to be released by that solution, that liquid, or that whatever this is that you're dealing with needs to be released from that system, right? When the question is how much heat in joules must be removed, you're not going to say negative 1317, because if that's how much needs to be removed, if you remove a negative, that's like adding to it. So if you already add the word removed to it, then the amount that needs to be removed is 1317. If you say what does the heat change need to be, then you want to make sure you include the negative sign, because this is heat that's going to be removed from the system. All right? And in terms of calories, well, there's 4.184 joules for every 1 calorie. So if we want to convert this to calories, for 1 calorie, so if we want to convert this to calories, 4.184 joules for every 1 calorie. So if we take that 1317 and divide it by 4.184, then we're going to get 315 calories. All right, 746, 1320, and 315. All right, and again, they had a negative sign back there because that is how much, that's the change. The change is negative, but the question asks how much should be removed. Then if you say remove a negative, again, that's like adding a positive. So 748. How many grams of water can be heated from 25 to 35 degrees Celsius by the heat released from 85 grams of iron that cools from 85 to 35 degrees Celsius? All right. So the iron cooled from 85 to 35. That's a change of 50 degrees. Okay. So change in temperature, 50 degrees Celsius. All right. And you can look at, I mean, that is energy being given off by the iron, right? So if you look at how much energy was given off there, from 85 to 35, so you're going to have a negative 50 degrees there, because the final temperature is 35, and final minus initial is how you find a change in temperature. All right? So 85 grams of iron, now we need to know the specific heat of iron. Okay? For example, where is the specific heat? There they are. Specific heat of iron. This is how many joules per gram degrees Celsius. And iron, it's 0.4498. And that was in our table on page 261. All right? 0.4498. That's how many joules per gram degrees Celsius. All right? So this will tell us how many joules of energy is given off of that by that iron. All right? So that's 85 times 0.4498 times negative 50. So this is how much energy, this is the energy change, negative 1,911.65. That's the energy change, and it's energy given off, right? Negative sign there. So how many grams of water can be heated to 25 degrees Celsius? So if we take that same number, all right, and we determine how many grams of water. Water is 4.184 joules per gram degree Celsius, and we can determine the change in temperature. Oh no, we're supposed to find out how many grams of water, and the change of temperature is 10 degrees Celsius here. All right, and it's going from 25 to 35. So final is 35 minus 25, so it's minus 10 here. And the grams of water, and again, the negative sign there is really only semantics at this point, because we are solving for how many grams of water can be changed 10 degrees, right? We don't care if this is actual heat giving off or being absorbed, because the grams, if we came up with a negative sign, we would say, oh, well, there can't be negative grams, right? So, I mean, yes, it's important to identify how the minus signs work, but if you're stuck and you can't figure that out, then you know grams has to be a positive number, right? Okay, so we have this value here. We can divide it by 10, divided by 4.184, and I'm getting 45.7 grams of water. All right, so 748. 45.7 grams of water. Okay, good. 750. All right, 750. A 5-gram mass of metal was heated to 100 degrees Celsius and then plunged into 100 grams of water at 24.0 degrees Celsius. The temperature of the resulting mixture became 28.0 degrees Celsius. How many joules did the water absorb? How many joules did the metal lose? What is the heat capacity of the metal sample? What's the specific heat of the metal? Okay, so 5-gram mass of metal was heated to 100 degrees Celsius and then plunged into 100 grams of water. So the first one is how many joules did the water absorb? And we can determine how many joules the water absorbed by looking at the water. 100 grams of water. Water is 4.184 joules for every gram degree Celsius, right? And the change in the temperature of water was, and then the plunge it to a temperature of 24, and the resulting mixture became 28. So it went from 28 is the final, 24 is the initial. So it's 28 final minus initial, 24. So that's a 4 degrees Celsius. 4 degrees Celsius is the change in temperature. So this is again temperature final minus temperature temperature initial equals change in temperature. Okay, so this will tell us how many joules of energy was absorbed by the water, right? And that's the question that's being asked. So we have 100 times 4.184 times 4. So that's 1,673 joules absorbed by the water. So this is 750, number 750, 1,673, 1,670 is what they rounded to. Okay, and second part, how many joules did the metal lose? Well, it has to be the same number, right? Because the metal is what released the energy. All right, so it is the same number. And then the next question is, what is the heat capacity of the metal? Well, if we choose the value, and the value here is 1673.6 before we round, and we don't need to round if we're going to answer another question with this value. This is joules, and you can tell it's joules because this was joules per gram degree Celsius. Grams cancel out, degrees Celsius cancel out, we're left with joules, right? So now the question is, what was the heat capacity of the metal sample? All right, heat capacity. So the equations that we've been working with here are mass, specific heat, change in temperature, and multiply all those together, and that gives you Q, heat. All right, so Q equals ms delta T, or we can also have Q equals C delta T, where C is the heat capacity of some system. Heat capacity just has units of joules per degree Celsius. All right. We don't know how many grams or anything about that specific system necessarily. We just know its heat capacity, which is joules per degree Celsius. So here we're looking for the, this is the Q joules of the metal block, right? And we're looking for the specific heat, or the heat capacity first, the heat capacity here. So heat capacity can be identified by taking the Q and dividing by the change in temperature. So the change in temperature for the block was final, 28, minus initial, 100. Right? The block was 100 degrees Celsius, dropped into 24 and became 28. So it went from 28 to 100, so it's minus 72. So C times a negative 72, that's the change in temperature, right? C times change in temperature equals 1673.6, which is the heat, and that's in joules. All right, so this is degrees Celsius. So joules per degree Celsius minus 72 degrees Celsius minus 72, oops, 72 degrees Celsius. And that'll be the heat capacity. But again, the heat capacity can't be negative, so heat capacity is always going to be a positive value. So we have 1673 minus, or not minus, divided by 72. 23.24, and that is joules per degree Celsius. All right, so that's the heat capacity, 23.24 joules per degree Celsius, 750 part C. Okay, and the last one, what's the specific heat of the metal? Well, I'm going to erase a little section here for ourselves. Q equals ms delta T or C delta T, right? So we can use this same Q here. We could put the mass of the brick, or I guess we don't know we could mass of the brick, which we know, the change in temperature, and solve for that. We just solve for the specific heat. So Q is, let's see. C, the units for C are joules per degree Celsius, and the units for MS are mass times joules per degree Celsius. So there's a way to tease it out of there. I'm not quite seeing it right now, but we can just use the 1673.6 joules as Q. The mass and specific heat is what we're trying to solve for, and change of temperature again was 72 degrees Celsius. All right, and so the specific heat, what was the mass of the block? 5 grams. So we have our 1673.6 divided by 5 and divided by 72. And so I'm looking at a specific heat of 4.65 joules per gram degrees Celsius. All right, so let's verify that in the back. 750D, 4.64 joules degrees Celsius. We can also try to look at our specific heats, our table of specific heats. Let's see if we can find that. There it is. Let's see if we can tell. 4.65, no, I don't see any specific heat, so I don't know what material it is necessarily. But specific heat is 4.65 joules per gram degree Celsius. All right, 752. Calculate the molar heat capacity of iron in joules per mole degrees Celsius. Its specific heat is 0.4498 joules per gram. .4498 joules per gram degree Celsius. Joules per gram degree Celsius. All right, and we want to know the molar heat capacity. We want joules per mole degree Celsius. I'm going to set this up like this: joules per gram degrees Celsius, and we want joules per mole degrees Celsius. So you can see we want grams on top and moles on the bottom, so that we can cancel out grams and get moles on the bottom, right? So we just need our grams per mole of iron. So for every 1 mole of iron, how many grams is that? 56.33, 55.85. 55.85 grams of iron for every mole of iron. So if we take 55.85 times 0.4498, then we get 25.12 joules per mole degree Celsius. All right, so that's just called dimensional analysis, right? Looking at the units and trying to get what we want to get, right? 752, 25.12. All right, 754, vat of 4.54 kilograms of water. 754. The water underwent a decrease in temperature from 60.25 to 58.65. 58.65 minus 60.25, right? So that's a change of negative 1.6 degrees Celsius. Delta T equals negative 1.6 degrees Celsius, right? Is that right? Did I do that right? 58.65 is the final, minus the initial 60.25. All right. How much energy in kilojoules left the water? All right, how many kilojoules in energy left the water? Well, it's 4.18. They say to use 4.18 joules per gram degrees Celsius. Joules per gram degrees Celsius. 4,540 grams of water. Grams of water. All right, and the change in temperature was minus 1.6 degrees Celsius. So we want to know how many joules left the water. 4,540 times 4.18 times negative 1.6. So the energy change is a negative 30,363 joules. And this many joules left the water, a positive 30,363. Again, this indicates the energy change relative to the system, but the answer is positive. So what was the question? How many energy in kilojoules, though? So 30.363 kilojoules, right? That's how much energy left the water. So that's 754, 30.4 kilojoules. All right, 756. Nitric acid neutralizes potassium hydroxide. To determine the heat of reaction, a student placed 55 milliliters of 0.13 molar nitric acid in a coffee cup calorimeter. Note that the temperature was 23.5 degrees Celsius, and added 50 milliliters of 1.5 molar potassium hydroxide, also at 23.5 degrees Celsius. The mixture was stirred quickly with a thermometer, and its temperature rose to 31.8. Final temperature 31.8. 31.8 minus initial temperature was what? 23.5. So a change in temperature 8.3 degrees Celsius. Write the balanced equation for the reaction. Calculate the heat of reaction in joules. Assume the specific heats of all solutions are 4.18 joules per gram degrees Celsius, and that all densities are 1 gram per milliliter. Calculate the heat of reaction per mole of acid in kilojoules per mole. Okay? We need to know the reaction, which is nitric acid plus potassium hydroxide. So HNO3 plus potassium hydroxide. Products are water and potassium nitrate. Okay? Looks balanced there. This is just monoprotic acid and monobasic base, right? So it's just a 1-to-1 ratio there. All right. Write a balanced equation for the reaction. Calculate the heat of reaction in joules. So we wrote the balanced equation. Now we want to determine the heat of reaction in joules. So we want to find the heat of reaction. Well, 4.184 joules per gram degrees. Okay. So, we're going to get back to finishing up this problem here. Chapter 7 review problem, 756. So we have nitric acid combined with potassium hydroxide. The products are water and potassium nitrate. This is how many joules it requires to move 1 gram of water 1 degree Celsius. Okay? So, let's see, 756. Let's reread how this reaction occurred. To determine the reaction, heat of reaction, a student placed 55 milliliters of 1.3 molar. So we have 55 milliliters, 1.3 molar. And in a coffee cup calorimeter, noted that the temperature was 23.5. So we have the change in temperature already, 8.3. And added 55 milliliters of 1.3 molar KOH. So 55 milliliters, 1.3 molar KOH. So this was the HNO3, and this was the KOH. Okay? So, the total volume is going to be 110 milliliters. And I'll say 110 milliliters of solution. And it says in there that we assume the density is 1, right? 1 gram per milliliter. And that's important because we need to know the mass of water, because our equation, again, is the mass of water times the specific heat of water, which is the 4.184, times the change in temperature. That's how we determine our heat, right? So the mass of water in this case is 110 grams, because there was 110 milliliters, and it's 1 gram per milliliter. 4.18. 4.18. Oh, they just said 4.18, so we'll just use the 4.18. 4.18 in the book here, joules per gram degrees Celsius. All right, and the change in temperature is 8.3 degrees Celsius. So this should be the heat of the reaction. Calculate the heat of the reaction in joules. Assume that the specific heat is that. Calculate the heat of reaction per mole of acid. So this is the heat of reaction here. And calculator. All right, 110 times 4.184 times 8.3. So that is, the answer to this problem here is 3,819 joules. All right. And let's see, this is calculate the heat of reaction in joules. So that's what we did. Assume that the specific heats of solution, calculate the heat of reaction per mole of units, per mole of acid in units kilojoules per mole. So we want to convert this into kilojoules per mole. So that's 3.819 kilojoules, 3.819 kilojoules. And we want it per mole. So we have to divide it by moles of acid that were added, right? Moles of acid. Well, there's 55 milliliters of 1.3 molar. So we can just take 0.055, that's how many liters there were, multiply it by 1.3, and that's going to be how many moles there were. So there was 0.0715 moles of HNO3. This is how many kilojoules, this is how many moles there were. This will give us an answer in kilojoules per mole. So, I'm getting 53.4 kilojoules per mole. So this is our first one, joules, heat of reaction, and then 53.4 kilojoules per mole. All right. So 7.56. Oh, and we have the reaction up there. 3,800. They rounded this up to 3,800, or down to 3,800, and this is 53.4 kilojoules per mole. So this value here, 3819, is the joules that the water, QW, right, the Q of the water. It's the joules of heat that the water received, right? And we know that because the water heated up. It received energy, right? Well, the reaction, the interaction between the nitric acid and the potassium hydroxide, that energy was released by the water, or by the reaction. This energy was released by the reaction. And this is how many kilojoules were released per mole. So when you're talking about the heat of reaction, this value has to be a negative value. This value, the Q for the water, is a positive value. But the question that they ask is, calculate the heat of reaction in joules. The heat of reaction in joules. So 3,819 isn't the heat of the reaction. 3,819 should be a negative 3,819 for the heat of the reaction, because the heat of the reaction is negative. All right, 757. No, 758. A 1 mole sample of propane gas was used for cooking in many rural areas. A gas used for cooking in many rural areas was placed in a bomb calorimeter with excess oxygen and ignited. The initial temperature of the calorimeter was 25 degrees Celsius, and its total heat capacity is 97.13 kilograms per degree Celsius. The reaction raised the temperature of the calorimeter to 27.282. 27.282 degrees Celsius, and that's our temperature final, our temperature initial. So that value minus temperature final minus 25. So the change in temperature equals 27.282 minus 25, 2.282. All right. The reaction rate temperature from 20 there to there. The heat capacity is 97.13 kilojoules per degree Celsius. 97.13 kilojoules per degree Celsius. And this is how many degrees Celsius, right? So if we multiply that by how many degrees Celsius, 2.282 degrees Celsius, then this will tell us how many kilojoules were released by that reaction. Write the balanced chemical equation for the reaction in the calorimeter. So the reaction is between propane, C3H68, C3H8, plus oxygen gas. Products are carbon dioxide and water. All right, let's try and balance this real quick. 3 carbons, 8 hydrogens needed. 4 waters there like that gives us 8 hydrogens here. Now we have 6, 7, 8, 9, 10 oxygens, so we have the 5 there. Is that right? 10 oxygens, 6, 7, 8, 9, 10, 8 hydrogens, 8 hydrogens, 3 carbons, 3 carbons. Okay. So, balance the equation. How many joules were liberated in this reaction? So this times that. 97.13, that's how many kilojoules per degree Celsius, and this is the change here. So it's 221.65 kilojoules. So if they're asking how many joules, the answer is going to be 221,000. How many joules were liberated in the reaction? What is the heat of reaction of propane with oxygen expressed in kilojoules per mole of propane? Well, it says 1 mole sample of propane, therefore it's that many kilojoules, and the heat of reaction is a negative value, right? So 758. Whoops, we got our wrong value there. Oh no, that's right. That's right. Good, we got it.